Hi everyone, welcome to the third and final lecture of Chapter 7. This is also the final lecture in Unit 3. As always, let's start with our not really attendance questions. Where does vitamin D in the body come from? What is the function of melanin? And what cells build new bone by calcifying cartilaginous tissue? Go ahead and try to answer those. Pause the video and see if you can come up with the answers. And let's see what those answers should actually be. Where does vitamin D come from? And here we're talking specifically about vitamin D that's already in your body. Vitamin D is made by your body by moving something that is essentially cholesterol into your skin. And once in your skin, when it's hit by ultraviolet B radiation, it's converted into an inactive form of vitamin D. And then that is transported mostly to the kidneys, but somewhat to the liver. And there it's converted into active vitamin D. Next, what is the function of melanin? Melanin, remember, is a pigment that blocks ultraviolet B radiation to prevent damage to our DNA. Now, hopefully that is kind of sparking a bit of a question as far as, well, melanin is there to block ultraviolet radiation, but ultraviolet radiation is needed to convert cholesterol into vitamin D. And actually, that is where skin color comes from. Skin color really is there to balance blocking so much ultraviolet radiation that we don't get skin cancer everywhere, but allowing enough through so that it can help with making vitamin D. That's why people that are from near the equator will have darker skin, like Central Africa area. People near the poles, like around Scandinavia area, will have very light skin. And that's because near the equator, where the sun is more intense, more risk of skin cancer is there. So the skin needs to be very dark. But up near the equator, up near the poles, there's very little sun intensity. So we have to have very pale skin, not block very much out at all, to allow enough through so that we don't become vitamin D deficient. What cells would build new bone by calcifying cartilaginous tissue? These are osteoblasts with a B. Remember, osteoblasts build bone. So let's start by talking about mineral deposition and resorption. Remember, we talked about bones were kind of like a bank. When we had more calcium and other minerals than we needed at the moment, we could store it in our bones. And when we needed that mineral later, we could withdraw it from the bone. Well, deposition is the part where we are depositing those minerals. And resorption is kind of like the withdrawal of those minerals. So mineral deposition or mineralization is how we are actually making bone. And it begins by the osteoblasts laying down collagen fibers. And it doesn't just lay them down any which way. If we go back, so here is an osteon, and the lamella are pulled apart here. And we can see these blue lines, which are the collagen fibers. In one of those lamellae, they run in one direction. And then the next, they run in another direction. And then the next, they run this direction again. So they're alternating. And these alternating layers produce this helical pattern that allows for bone to be much stronger than if they all ran the same direction. And once these collagen fibers are laid down by the osteoblasts, next the osteoblasts begin laying down those hydroxyapatite minerals that we talked about onto the collagen fibers. And as those hydroxyapatite are laid down onto the collagen fibers, there are these small crystals that we call seed crystals. And the process is kind of like if you've ever made rock candy. You start with just a few little crystals of sugar on a string, but then more and more and more sugar crystals start to build onto that. Well, the hydroxyapatite crystals or the seed crystals do the same thing. Once they are deposited onto the collagen, other minerals will start to grow, and those crystals will start to get larger and larger and larger, mineralizing and hardening this bone. Now, sometimes we'll actually have a similar process occur where it's not supposed to, and we call this ectopic ossification. Ectopic just means out of place. So you've all heard of an ectopic pregnancy. This is where a baby is developing outside of the womb, outside of the uterus. Well, ectopic ossification is when this hardening process, this calcification, is happening in an otherwise soft tissue. And what happens is it starts to develop this mass called a calculus. A calculus is just a calcified mass in an organ that is meant to be soft. This can happen in places like the stomach or the lungs. And it's kind of almost like if a bone was starting to grow in one of these organs. That's kind of what it would be like. Now, so far we've been talking about deposition or mineralization. And this is that taking minerals out of the blood and putting it into the bone. But the other is mineral resorption. And resorption is when we're breaking bone down using those osteoclasts. And as the bone is broken down, those minerals are spilling out of the bone into the blood, raising your calcium levels. And a lot of the goal here is to maintain calcium homeostasis. We're supposed to have a very narrow range of calcium in our body, in our blood. If it gets too high, we call that hypercalcemia. If it gets too low, we call that hypocalcemia. Remember, hypo means low or under or below. Hyper meant excess or above. So hypocalcemia is not enough calcium. And this can lead to things like nervous excitability. The neurons are sending signals too quickly, too easily. And the result of that can be things like muscle spasms, muscles contracting when we don't necessarily want them to, or tetany, which is when muscles cramp up, they contract and stay contracted. Hypercalcemia, on the other hand, when we have too much calcium, this can lead to nervous depression. And that doesn't necessarily mean like sad. That means that your nerves are not sending those signals successfully. Not all of them are getting fired, or they're going too slowly. But that's nervous depression. And this can lead to things like various mental disorders. It can lead to muscle weakness. It can lead to cardiac arrest, which is heart failure. So let's talk about how we maintain calcium homeostasis. Well, vitamin D plays a role here. Vitamin D, specifically vitamin D3, which is calcitriol, but we're just going to call it vitamin D. And vitamin D does a few different things to help with calcium homeostasis. First, at the small intestines, vitamin D is needed by the small intestines to allow us to absorb calcium from what we eat or drink. Let's say we sit down and we drink a glass of milk, and we know milk has a lot of calcium in it. But if we did not have adequate vitamin D in our body, the calcium in that milk would actually pass straight through and it would leave in our feces. Vitamin D tells our small intestines to absorb calcium from whatever we eat or drink. Next time you're at the store, when you look at milk in the case, almost always you'll see that it is vitamin D fortified. And the reason that they do that is rather than I wonder if this person is going to drink this milk has enough vitamin D that they'll absorb this calcium. They're going to add some vitamin D to it so that they know that you'll absorb the calcium. Vitamin D is also going to increase bone resorption, bone breakdown, by stimulating osteoclast proliferation. That just means that it's going to cause there to be more osteoclasts, the cells that break bone down. Remember, resorption or breaking bone down, that's not necessarily a bad thing. We are constantly building bone and breaking bone down. They're just happening at the same rate. So we do need bone to be broken down regularly. Also, and this is just a minor role, it doesn't do this very much, but we want to mention it, vitamin D tells your kidneys to reabsorb calcium before it leaves your body as urine. So the way your kidneys work is they're going to pull a lot of stuff out of your blood. Some of that stuff is going to leave the body as urine. But some of that stuff your body could still use, so your kidneys reabsorb it. It moves back into the blood so that it does not leave the body. And kidneys will naturally reabsorb some calcium. But vitamin D tells them to reabsorb a little more calcium. Now, this is not a big thing that calcitriol or vitamin D does. Instead, there's going to be another substance that we talk about that does this a lot more. So here we have, from a different textbook, a chart that should look kind of familiar. This is our homeostatic feedback loop, and specifically this is one for calcium. And up at the top, we have what happens when there is hypercalcemia, excess calcium. Down at the bottom, we have what's happening when there is hypocalcemia, or low calcium. So let's see what exactly happens. When there is hypercalcemia, when there's too much calcium in the blood, the thyroid gland, a gland that's in your neck, detects that. Specifically, there are some cells called parafollicular cells, or clear cells, or sometimes just called C cells. But the thyroid gland detects that and releases a hormone called calcitonin. Calcitonin levels in your blood rise, and calcitonin does a couple of things. One, it's going to inhibit osteoclast activity with a C, and it's going to stimulate osteoblast activity with a B. So we are stimulating the cells that build bone. And as we build bone, what building material do we need? Calcium and other minerals. So the cells are going to start to take calcium out of the blood and put it into the bone. Calcium levels in the blood drop until we're back to normal. But what happens if we get hypocalcemia? If our blood calcium levels get too low? Well, this is detected by, we have these little nodules on the back or on the posterior surface of the thyroid gland called parathyroid glands. Parathyroid glands detect hypocalcemia, and they release something called parathyroid hormone, or PTH. Parathyroid hormone levels in your blood rise, and parathyroid hormone actually does several things. Two of them are exactly the opposite of what calcitonin did. It's going to stimulate osteoclast activity and inhibit osteoblast activity. So now we stop building bone and we start breaking bone down, bone resorption. And as osteoclasts break bone down, calcium and those other minerals spill out into the blood, raising blood calcium levels back to normal. And think way back to the very first lecture when we talked about homeostasis. We said that it was dynamic equilibrium, and that meant that even though there was this level we were constantly going too high and too low, and too high and too low, but overall, we were kept in balance. And that's exactly what we see here with calcium. Now here's pretty much the same thing, but shown completely differently. This is how your book shows what we just talked about. Over here on the left, this is what calcitonin does. Over here on the right, this is what parathyroid hormone does. And I said there were a few different things that parathyroid hormone did. Well, we talked about what it did with osteoclasts and osteoblasts. But it does a couple of other things also. One, it enhances vitamin D synthesis at the kidneys. So it tells the kidneys to activate more vitamin D. And we saw what vitamin D does. And also, it tells the kidneys to reabsorb more calcium. It also does some stuff with phosphate, but that's not important here while we're talking about calcium. So, we're going to increase calcium reabsorption. All of these things are going to raise blood calcium levels. Now, before we go on, I do want to briefly point out something that not a lot of sources talk about, and that's really that calcitonin does not play much of a role in an adult. It does do all those things if it is in really high levels, but for the most part, calcitonin is only really active in children. It's parathyroid hormone that is really responsible for calcium homeostasis. It's still good to know what calcitonin does. It's just most of the time it's not that active in an adult. And this from your textbook on figure 714 kind of sums up all of what we've been talking about with vitamin D and calcitonin and parathyroid hormone. This is all of that together. But there are other hormones at work also with bone. It's just now we're going to be talking more about bone growth or bone building as opposed to just the calcium side of things. And we're going to not talk about all of those hormones, just some of the bigger ones. First, growth hormone. Growth hormone we've probably all heard about because especially in sports and around the Olympics we hear a lot about growth hormone. But growth hormone is something that naturally is released from a part of your brain called the anterior pituitary gland. It is an anterior pituitary gland hormone. And it really causes growth throughout the body. Here, in this chapter, we're going to talk about skeletal growth. And oddly, growth hormone does not stimulate bone growth. What it does is it stimulates cartilage growth and it stimulates that conversion from cartilage into bone. So we do end up with more bone. We end up with bone growth, but not directly. So, what happens if there's too much growth hormone? There's a couple of disorders, both of which result from excess growth hormone. One of them is called acromegaly, and one of them is called gigantism. Gigantism is what happens when you have too much growth hormone from childhood. Acromegaly is what happens when you have too much growth hormone, but it doesn't start until after you are an adult. And that's what we see here. In this picture on the left, the shorter man is just a man of average height. And the tall person standing next to him has gigantism. And you can see that the man with gigantism is significantly taller, almost twice as tall it looks like. But if we look at the tall man, he's pretty proportionate. Like his arms look the right length for his height. His hands look the right size for his height. Of course, his arms are longer than the other guy. His hands are bigger than the other guy. But for his height, everything looks in proportion. Now let's look over here on the right. The man with the epic mustache is a man of average height, pretty average build. And the man with the shaved head has acromegaly. This is excess growth hormone, but it didn't start until after adulthood. Now, if we look at the man with acromegaly, he's about the same height. He is of average height. But we can look, and it's maybe a little bit tough to put our finger on it, but something is going on. So what's happening here? Well, first let's look at their heads. The man on the right with the shaved head, his skull is much larger than the man with the mustache. If we look at their hands, well, his thumb and his fingers are very, very thick. His hand is very large. If he wasn't wearing this robe, we would see that his elbows and his wrists and his knees and ankles would all be very large. And those are all signs of acromegaly. Average height, but very thick bones and very large skull. So, let's use that as a thinking cap question. Anterior pituitary gland oversecretion of growth hormone results in gigantism or acromegaly, depending on the age of onset. Both of them are oversecretion of growth hormone. One is as a child, one is it doesn't hit until after adulthood. So why are the two conditions different? Think about that and see if you can come up with an answer. Well, it's going to have to do completely with that epiphyseal plate, epiphyseal line thing that we talked about in the previous lecture. As a child, up until early adulthood, you have an epiphyseal plate, and we still have active lengthening of bone. And growth hormone increases that lengthening. If there is excess growth hormone, then that lengthening will occur a lot more. And that's what we see over here with gigantism. Now, he will continue to grow, and he got this height before his epiphyseal plates closed. So this happened all until he was about the age of adulthood. After that, he's not going to get any taller. Over here on the right, with acromegaly, his epiphyseal plate had sealed into the epiphyseal line, and then he started having excess growth hormone. It doesn't matter how much growth hormone or any other hormone you have, once those epiphyseal plates close into a line, you're not going to have any length increase in bone. But we can still have those bones get thicker, get larger in diameter or in thickness. So that's what we see here with acromegaly. Now, as kind of a couple of side stories, some people with gigantism also develop acromegaly after adulthood. I don't know the case of this gentleman here, but there is someone famous most people have heard of, especially if they were around in the 80s and 90s, and that is Andre the Giant. Andre the Giant had gigantism. He was incredibly tall. When I was a child, I was really big into wrestling, and I met him at Rupp Arena once. And in middle school, I came up to about his waist. He was truly gigantic. But he also had a really large head and really thick limbs and fingers. He was kind of built like this man, but much taller. And that's because he continued to have hypersecretion of growth hormone even after he was able to stop getting taller. So it depends on whether or not the growth hormone continues to be in excess. Also, I have a neighbor across the street, and when I moved into the house that I'm in, he was pretty young, and his mother, who has some issues, was driving, and they got into a car accident, and he hit his head. And that's one of the ways that you can cause hypersecretion from the anterior pituitary. There's a lot of different hormones that come from that spot. And if you have head trauma, you can get hypersecretion. In his case, that's exactly what happened to him. He was in the wreck, he hit his head, and he started developing excess growth hormone. And by the time he was in high school, he was over 7 feet tall. He still lives across the street from me now. He's about 22 or 23, and he is really, really tall. I would say he's probably about 7'6" or 7'7". And he was that way, right around the end of high school. Okay, so let's talk about some other hormones, the sex hormones, estrogen and testosterone. Both males and females release both estrogen and testosterone. It's just males have more testosterone, females have more estrogen typically, but both release both hormones. And these sex hormones, as you are nearing puberty, you start to have fluctuations. You'll start to have rise and drop, rise and drop. And once you hit puberty, you have a very sharp rise. And we talked about this previously with the epiphyseal plate. That's what the growth spurt is. Or usually there's more than one, because of that rise and fall, and then at puberty you have the real sharp rise. And then shortly after puberty, those levels drop back down, and as they drop back down to a more normal level, that causes the epiphyseal plate to close into the epiphyseal line, and after that point, there is no more growth in length. Now let's talk about fractures. And there are different ways to classify fractures. We're going to talk about several different ways, although there are more than what we will talk about. First, we have stress fractures versus pathological fractures. A stress fracture results from some sort of trauma to the bone. Let's say you accidentally hit your thumb with a hammer, or you're playing football and you get hit and your leg breaks. Those are stress fractures. Pathological fractures are the result of weakened bone from something like either osteoporosis or hypocalcemia or cancer, certain medical treatments, anything that causes the bone to be weakened, and then the break is the result of that weakening. We can also classify fractures by these methods here. The position of the ends of the bone after the break. For example, if we have a break where the ends of the bone are no longer lined up with each other, that's a displaced fracture. The opposite of that would be a non-displaced fracture, and that's when the bone breaks, but the broken bits are still lined up with each other. The broken ends of the bone are still in the same position. Another way is by how complete is the break. A complete fracture is a fracture that crosses the entire bone, whereas an incomplete fracture, the break does not cross the entire bone. And this kind of very brutal looking break that we have over here is going to talk about whether the break is open or closed. We're talking about skin penetration. If the bone penetrates through the skin, it is an open fracture. If it does not, then it is a closed fracture. So using these three methods, how would you classify the break that we see over here? Well, the bone positions are out of place, so it's a displaced fracture. It has to be complete in order for us to see this bone sticking through. And since it's poking through the skin, it is open. This is a displaced fracture, a complete fracture, and an open fracture. Now, let's look at some methods that we can classify fractures using a table from a different textbook. Some of these are in your book, some of them are not. And again, this is by no means all of the fractures, but let's look at some of them. One is called a comminuted fracture, and this is common in the elderly or people with brittle bones. And what happens is during the break, the bone kind of shatters. It breaks into 3 pieces or more, and that's what we see here. Next, compression fracture. This is also common in the elderly or people with osteoporosis. It's also common in a fall. So when you fall and the bone is compressed, it again kind of shatters, but it's in a very specific way. This happens in porous parts of bone, such as the body of a vertebrae like we see here. Next is a spiral fracture. This is really common in sports. For example, if you jump to catch a ball and as you land, you're pivoting. When your leg hits, that torque, that twisting motion, results in a spiral fracture. Over here we see an epiphyseal fracture. And this is a break at the epiphyseal line or epiphyseal plate. So at the epiphyseal plate, there is that layer of cartilage which is weaker than the surrounding area. So there's going to be a break at the weakest point. Now at the epiphyseal line, this is much less common, but there's still that scar area there where there's a little bit less strength, so we can still see this type of break there, although it's much more common in an epiphyseal plate. A depressed fracture, common on the skull. If something lands and hits you on the head, it pushes the bone in. That's a depressed fracture. And finally, what I think personally is the saddest one is called a green stick fracture, and this happens in young children whose bones have not fully hardened. So children, basically, their skeleton is a lot of cartilage. It's not fully calcified bone. They're kind of like made of rubber. But as their bone starts to harden, it doesn't do so smoothly all over. Certain parts of it will harden, other parts will remain soft. And if a bone breaks, it's kind of like if you take a twig off of a tree and you break it. Well, the woody part of that twig breaks really easily, whereas the living part, the green part of that twig, doesn't break. It kind of holds on. Well, the bony part, the hardened part of a child's bone will break and shatter, whereas the cartilage part will still hold on. And that's what a green stick fracture is. Well, if you get a fracture, how is it fixed? Well, probably you're going to go to the doctor, and the doctor is going to figure out the best way to treat this. And we can get something called reduction. And there's two different ways of reduction. One is called closed reduction. And this is when the doctor just manually or with his hands positions the bone back into its normal position so that it can heal properly. But depending on the location or the severity of the break, you may get open reduction. And this is once the bone is pushed back into place, we have to use pins or screws or wires to hold the bone in place as it heals. So how does the bone heal? That's what we have up here. This is repair of a break. And first, when a bone breaks, remember we saw that bones have a lot of blood vessels. So as we break the bone, we also break the blood vessels. And the bone starts to bleed, and the blood is trapped within those membranes that we learned about. This is called a hematoma. Hematoma really is just bruise. We learned that back in skin. Hematoma is bleeding under the skin. So here, the hematoma is bleeding around the bone. And that blood, as it starts to fill up this area, it's also going to fill up with osteogenic stem cells. And the osteogenic stem cells are going to start to lay down some fibrous tissue called granulation tissue. Once we have that in place, the osteogenic cells are going to start laying down collagen. Some of the osteogenic stem cells are going to produce chondrocytes, cartilage cells. And those cartilage cells are going to produce fibrocartilage in this area. called the soft callus. And the soft callus is going to persist for quite a while. But within that soft callus, we're going to have some osteogenic stem cells that produce osteoblasts. And the osteoblasts are going to start laying down ossification tissue. So the outer edge is going to harden into bone called the hard callus. This is just protection for everything that's going on underneath. Once we have this ossified area, this hard callus in place, those osteoblasts are going to start laying down spongy bone inside. And that spongy bone is eventually going to be converted to compact bone. And we end up with this mostly repaired bone. Once we get to this state, we're going to have bone remodeling. Bone remodeling is continuing to lay down more bone in the weak spots and resorbing bone in these extra areas here left over from the hard callus. All right, so there are some disorders here in this chapter that you are responsible for doing either by using your textbook or online or some other resources. So make sure to do those as part of self-study. This is the end of Unit 3, so coming up next is Lecture Exam 3. And Lecture Exam 3 is going to focus on Chapter 6 and Chapter 7. There's going to be some older material there as well, but the focus is everything that we've done since Exam 2. Once we get done with that, we're going to start nervous. Nervous will come after Exam 3, but I advise you to start working on it early because nervous and muscle, our next two chapters, are two of the most intense. So get an early start on those. If you have any questions at all, let me know. Otherwise, I'll talk to you after the exam.